So picking up with number 5, 3 identical masses M lie along a line and are connected by 4 identical springs of spring constant K, where we have wall K, M sub 1, K, M sub 2, K, M sub 3, K, wall. Let x sub 1, x sub 2, x sub 3 denote the small longitudinal displacements of the 3 masses from equilibrium. The walls are fixed, so we may regard x not equal 0, x sub 4 equals 0. So A, determine the kinetic and potential energies. B, determine the mass and stiffness matrices. C, determine the normal mode frequencies. D, determine the normal mode shapes. And E, determine the general motion. So this is a small amplitude vibrations problem. So for part A, kinetic and potential energies, we can say that the kinetic energy is T equals 1/2 m times this quantity x sub 1 dot squared plus x sub 2 dot squared plus x sub 3 dot squared. And the extensions of the 4 springs are respectively x sub 1, x sub 2 minus x sub 1, and x sub 3 minus x sub 2, and negative x sub 3. And because the last spring's energy depends on the square of its extension, it contributes k x sub 3 squared divided by 2. So therefore V equals 1/2 k x sub 1 squared plus 1/2 k times quantity x sub 2 minus x sub 1 squared plus 1/2 k times the quantity x sub 3 minus x sub 2 squared plus 1/2 k x sub 3 squared. So from there, V equals k over 2 bracket x sub 1 squared plus the quantity x sub 2 minus x sub 1 squared plus the quantity x sub 3 minus x sub 2 squared plus x sub 3 squared, close bracket. Then expanding from that, we get the following. V equals k over 2 times this whole quantity in the brackets, x sub 1 squared plus x sub 2 squared minus 2x sub 1, x sub 2, plus x sub 1 squared plus x sub 3 squared minus 2x sub 2, x sub 3 plus x sub 2 squared plus x sub 3 squared. And that's going to equal k over 2 times this quantity, 2x sub 1 squared plus 2x sub 2 squared plus 2x sub 3 squared minus 2x sub 1, x sub 2, minus 2x sub 2, x sub 3. So from there, V equals k times quantity x sub 1 squared plus x sub 2 squared plus x sub 3 squared minus x sub 1, x sub 2, minus x sub 2, x sub 3. Close bracket there, and the Lagrangian is going to be T minus V. So that is part A. Part B, we want to determine the mass and the stiffness matrices. So building on this for part B, so the mass and stiffness matrices, define the displacement vector x equals this column x sub 1, x sub 2, x sub 3. And the energies can be written as the following. T equals x dot transpose m x dot. V equals 1/2 x transpose k x. And the mass matrix is M equals lowercase m. And then we have first row here of this matrix 1, 0, 0, second row 0, 1, 0, third row 0, 0, 1. And the stiffness matrix is that capital K equals K. And then 2, negative 1, 0, negative 1, 2, negative 1, 0, negative 1, 2 for those rows respectively. So from here, therefore the equations of motions are capital M x double dot plus kx equals 0, and explicitly m x sub 1 double dot equals negative 2kx. M x sub 2 double dot equals kx sub 1 minus 2kx sub 2 plus kx sub 3, and mx sub 3 double dot equals kx sub 2 minus 2x sub 3. Okay. Moving along to letter C, we want to find the normal mode frequencies. So look for the form x of t equals ae to the I omega t, where a is this column, a sub 1, a sub 2, a sub 3, the vector. And so x double dot equals negative omega squared x. Substitute into the equations of motion in k minus omega squared capital M, that quantity there, times a equals 0. And a non-trivial solution requires the determinant of this k minus omega squared capital M equals 0. So to find the dimensionless eigenvalue, lambda equals m omega squared k, and the characteristic equation becomes a determinant. Here, first row, 2 minus lambda, -1, 0. Second row, -1, 2 minus lambda, -1. Third row, 0, -1, 2 minus lambda, and that's set equal to 0. So expanding along the first row, 2 minus lambda times this determinant here of this component, 2 minus lambda, -1, -1, 2 minus lambda, minus -1 times -1, -1, -1, 0, 2 minus lambda, the determinant of that equals 0. That's just but standard determinant operations. Okay, so you set that equal to 0. And now from here, what we're going to have, continuing with part C, we have the following: 2 minus lambda times the quantity in brackets, that 2 minus lambda squared minus 1 times that 2 minus lambda equals 0. So therefore, quantity 2 minus lambda bracket quantity 2 minus lambda squared minus 2 close bracket equals 0. So we're going to wind up with 2 minus lambda equals 0, or 2 minus lambda squared equals 2. So we have three eigenvalues. Lambda sub 1 equals 2 minus square root of 2. Lambda sub 2 equals 2, and lambda sub 3 equals 2 plus square root of 2. And since lambda equals m omega squared over k, the square normal mode frequencies are omega sub 1 squared equals k over m times the quantity 2 minus square root of 2. Omega sub 2 squared equals 2k over m, and omega sub 3 squared equals k over m times the quantity 2 plus square root of 2. So taking the positive square root of these respectively, and just take, we get omega sub 1 equals square root of k over m times quantity 2 minus square root of 2. Omega sub 2 equals square root of 2k over m. Omega sub 3 equals positive square root of k over m times the quantity 2 plus 2 square root of 2. So these can also be expressed in the standard fixed chain form. Omega sub j equals 2 times square root of k over m sine of j pi over 8, where j equals 1, 2, and 3. Okay, so that's part C. Moving along to part D, we want to find the normal mode shapes. So first normal mode for lambda sub 1 is 2 minus square root of 2. And we have 2 minus lambda sub 1 equals square root of 2. So the eigenvalue equation is going to be this. Matrix there, square root of 2, -1, 0, -1, square root of 2, -1, 0, negative, whoops, sorry about that. I'll just take this off for a second. So going back here, sorry about that. The eigenvalue equation is, for this matrix here, first row, square root of 2, -1, 0. Second row, -1, square root of 2, -1. Third row, 0, -1, square root of 2. Times this column, a sub 1, a sub 2, a sub 3 equals 0. So performing the computation here, so square root of 2, a sub 1 minus a sub 2 equals 0. So a sub 2 equals square root of 2, a sub 1. That's for the first row. Third row gives negative a sub 2 plus square root of 2, a sub 3 equals 0. So a sub 2 equals square root of 2, a sub 3. So a sub 3 equals a sub 1. And continuing there with letter D. So convenient eigenvector here is going to be that first eigenvector A, or A superscript 1 here is proportional to that 1 square root of 2, 1 column. And a normalized version here, that E superscript 1, or first normalized mode vector, that's going to be 1/2 times that column 1 square root of 2, 1. And the qualitative shape, all three masses move in the same direction. The middle mass has the largest amplitude, plus, 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 and this is the lowest frequency mode. So moving along to the second normal mode, for lambda sub 2 equals 2, the eigenvalue equation becomes this matrix: 0, -1, 0, 1, -1, 0, -1, 0, -1, 0 for the three rows respectively, times this column, a sub 1, a sub 2, a sub 3 equals 0. So the first row gives a sub 2 equals 0. Second row gives negative a sub 1 minus a sub 3 equals 0. And so a sub 3 equals negative a sub 1. So we have here the second eigenvector A proportional to 1, 0, negative 1 column there. And a normalized version is here. Second normalized mode vector equals 1 over the square root of 2 times that column of 1, 0, negative 1. And our qualitative shape here, the two outer masses move with equal amplitudes in opposite directions, while the middle mass remains stationary and plus 0 minus. So the center mass is a node of this mode. So the third normal mode for lambda sub 3 is 2 plus square root of 2. 2 minus lambda sub 3 equals negative square root of 2. We have the eigenvalue equation is here. First row, the matrix, negative square root of 2, negative 1, 0. Second row, negative 1, negative square root of 2, negative 1. And third row, 0, negative 1, square root of negative 2. Times that this column, a sub 1, a sub 2, a sub 3 equals 0. The first row gives negative square root of 2, a sub 1 minus a sub 2 is 0. So a sub 2 equals negative square root of 2 times a. And the third row gives, a sub 1. So a sub 2 equals negative square root of 2, a sub 1. And the third row gives negative a sub 2 minus square root of 2, a sub 3 equals 0. And using a sub 2 equals negative square root of 2, a sub 1. Square root of 2, a sub 1 minus the square root of 2, a sub 3 equals 0. So a sub 3 equals a sub 1. And building on that, so we have here that third eigenvector A is proportional to this column 1, negative square root of 2, 1, and a normalized version here. That third normalized mode vector equals 1/2 times that column 1, negative square root of 2, 1. And the qualitative shape, the two outer masses move together while the middle mass moves oppositely with larger amplitude plus minus plus. And this is the highest frequency mode because adjacent masses move most strongly against one another, producing the greatest spring deformation. And for part E, finding the general motion. The general motion, because the normal vectors form a complete orthonormal set, the most general motion can be written as the following. So we have this x of t equals this sum of j equals 1 to 3, q sub j of t in this normal mode, first normalized, jth mode here, normalized mode, that jth normalized mode vector, where each normal coordinate satisfies that q sub j double dot plus omega sub j squared q sub j, and that equals 0. So we get q sub j of t equals a sub j cosine omega sub jt plus b sub j sine of omega sub jt. So x of t is going to equal the following: this sum from j equals 1 to 3, and then bracket a sub j cosine of omega sub jt plus b sub j sine of omega sub jt, close bracket, in that normalized mode vector, that jth normalized mode vector. And the constants a sub j and b sub j are determined by the initial displacements and velocities. Okay, so that's problem number 5. Thank you very much and have a great day.